Good afternoon, my name is Aisling Murphy and I'm a PhD student studying with Dr Emma Whelan in Univ University in Ireland. I'm going to discuss some of the work we've been doing which shows how it may be possible to use the properties of jets from young stars as an indirect detection method for planets in the disk. Now, as an example of the jets that we're discussing, we have the striking bipolar jet HH30, and this shows the jet being launched from the poles perpendicular to the accretion disk. Bipolar jets like these are common features in young stars, and they're linked to the accretion of material from the disk. As well as playing a key role in the formation of the star, they may shape the composition and structure of the protoplanetary disk, both by removing angular momentum from near the launching region, and by irradiating the upper layers of the disk. As we'll see, studying these jets can also give us important clues about what's happening in the inner region near the driving star. For my research, I'm looking at SC102 or TH28, a young Tauri star about 160 parsecs away from us. As you can see from the composite image here, it has a striking bipolar jet aligned close to the plane of the sky. This means that we view the star through the edge-on disk, and therefore the stellar spectrum is strongly veiled. Another notable feature for this jet is that the spectra of the microjets close to the star show signs that they are rotating around their axis. This is significant because it is a key prediction of jet launching models, but it could also be mimicked by other features, for example if the jet is precessing. So the observations that I'm working with were taken with MUSE, the multi-unit spectroscopic explorer on the VLT. This is an integral field spectroscopy instrument, so it takes a wavelength spectrum for every pixel in the field of view, and this allows simultaneous acquisition of images and spectra. This lets us look at the morphology, the physical conditions, and the kinematics of the jet at the same time. MUSE covers the optical to near-infrared range with medium spectral resolution, and has 0.2 arc-second sampling over a 1x1 arc-minute field of view. It now has adaptive optics correction available, but our observations were taken in 2014, so they are seeing limited to a resolution of 0.9 arc-seconds. For this research, we're focusing on the microjets close to the star, the region illustrated by these spectra images. So we have H-alpha emission in the upper panels and sulfur-2 in the lower panels. On the left-hand side, we have the high-velocity blue-shifted channel with the blue-shifted jet seen there, and on the right-hand side, we have the high-velocity red-shifted channel, so we have the red-shifted jet there. Now, the orientation of the jet means the velocity ranges of the red and blue lobes overlap, so we can see them both in the low velocity channel in the middle. And we can already see the morphological differences between the two microjets, so we have the relatively broad blue shifted jet with these large bow shock structures compared to the relatively bright and collimated red shifted jet with much more compact knots. As well as looking at the overall structure, we fitted the centroids along the axis of the jet to see how the position of the jet varied along the direction of flow. Again, the blue shifted jet is on the left-hand side and the red shifted on the right, with the plot centered on the star. And if we look at the centroid positions in the inner 6 arc-seconds, what we find is a small but consistent wiggle along both sides of the jet. Now, it's consistent between different emission lines, and we see it best in nitrogen 2 because this traces only the fast inner region of the flow. The other lines suffer contamination from low-velocity components, but we see a similar pattern there. We can also see from the error bars that the blue jet is significantly fainter, but very strikingly we see a very clear point symmetry between the wiggle on both sides of the jet, and this is really interesting. What could be causing this wiggle? Now, wiggles like this have been observed in other jets, for example in HH30 and DG tau, and they're typically interpreted as the signature of a possible companion object. So there are two mechanisms for how this can happen: orbital motion, where the gravitational pull of the companion pulls the jet source back and forth, resulting in a plane symmetric wiggle, like in the top image here. Alternatively, you could see a precession wiggle if there's a companion orbiting on a plane that's inclined to the accretion disk. In that case, we see tidal forces in the inner disk which cause the jet to precess around its axis. And in that case, we see a wiggle with a point symmetric structure, which of course matches what we see in TH28. This is significant because we don't normally expect to see precession signatures on such a small scale, and also because typically when looking at wiggles like these, we aren't able to observe a wiggle in both sides of the jet at once. Usually one of the jet lobes, usually the red-shifted lobe, is obscured or fainter, and therefore it's quite exceptional that we're able to trace a wiggle back so close to the source in both lobes of the jet simultaneously. So our next step was to fit a model to the wiggle and see what we could find out about the underlying system. So for a precessing ballistic jet, we have this relationship here for how the shape of the jet in the plane of the sky changes over time, and it's related to nu, our precession frequency, to beta, the half opening angle of the precession wiggle, and also to Vj, the jet velocity, which we can constrain from other observations. Now, if this wiggle is caused by a companion, we then have a theoretical relationship between the orbital period and the precession period. And here we have mu, which is the ratio of the companion mass to that of the total system, and sigma, which is the ratio of the inner disk to the binary separation, because we expect that there is going to be an outer circumbinary disk and then an inner disk that's truncated to some fraction of the separation between the two objects. Now we have an additional constraint, which is that we know the effective orbital motion should be much smaller than that caused by the precession. This gives us a condition for the maximum orbital velocity based on the opening angle of the precession and also the jet velocity. And then combining this with our estimated orbital period, we can get a maximum orbital radius for the companion. We can then use Kepler's third law to estimate the total mass of the system and compare this with existing estimates for TH28 to see if it's realistic. So we fitted our model to the wiggles in several different emission lines. We fit the red and blue lobes separately because we know they have different jet velocities, and based on other observations we take our velocity as 270 km a second for the red-shifted jet and 360 km a second for the blue-shifted jet. In all cases we find quite consistent fit parameters, with nu being between 0.7 and 0.9 inverse years, hence a precession period of 7 to 9 years. We find a slight difference in opening angle between the two jets, with beta being 0.5 to 0.6 degrees in the red-shifted jet and 0.7 to 1 degree in the blue-shifted jet. This is consistent with what we already know about the morphology of the microjets, but it might also be due to the blue-shifted jet being relatively faint, as we mentioned, and also relatively short, so we have a lesser extent of the jet to fit compared to the red-shifted jet. This means that it might be harder to accurately fit the wiggle parameters. Our wiggle parameters then give us estimates for the maximum orbital velocity of a companion, but to infer anything more we need to make some assumptions about the relative mass of the companion and how much it truncates the inner disk. We take the parameters from the nitrogen 2 red-shifted jet because this is the best constraint, but as mentioned our fits are very consistent and we expect these parameters to be representative in all cases. We consider three scenarios: a stellar mass companion of about 0.2 solar masses, with sigma taken to be 1/3, which is a standard theoretical value. We'd also consider a brown dwarf of about 0.08 solar masses, and a Jupiter mass companion of 0.001 solar masses. In the last two cases we expect to have a very different scenario, where the binary separation is so small that the companion orbits close within the accretion disk itself, resulting in a broken disk scenario where sigma is close to 1. Previous observations indicate that TH28 has a mass of about 1.6 solar masses, so how do our hypothetical systems compare? Well, if we look at the stellar mass companion scenario, we find a system mass of about 0.04 solar masses, which is way too small. If we look at a Jupiter mass companion, we get a system mass of over 8,000 solar masses, which is far too big. However, if we consider a brown dwarf companion, we get a system mass of about 1.2 solar masses, which is just about right and makes this the most likely scenario. So if we consider both the red and blue shifted jets and take a companion of 150 Jupiter masses, we find an estimated system mass of 0.5 to 2.7 solar masses, with an orbital period less than 135 days and a binary separation of 0.4 to 0.7 AU. This is not out of the question for a brown dwarf companion. However, we have some important caveats to consider. First, the orbital velocity we obtain is an upper limit. We expect the true value to be smaller, implying a closer orbit and smaller companion. We also note that the wiggle we observe is on a small scale compared to the scene, which may hinder an accurate fit of the wiggle parameters. In particular, we know that the orbital parameters are very sensitive to the half-opening angle beta, which is a small but significant discrepancy between the two jets, and it's unclear how much of that is due to a genuine difference in the shape of the jets, and how much is due to the faintness of the blue jet. We also consider how our findings compare to observations of the disk around TH28. Now, NACO observations rule out a companion at distances greater than 30 AU, which of course is much larger than the separations that we are looking at. ALMA observations also don't suggest any large discontinuities between the inner and outer disk regions, but might not rule out a broken inner disk very close to the star. To conclude, we find a striking wiggle in the microjets of TH28 that may suggest precession due to a very close brown dwarf companion. However, a strong alternative hypothesis is that this precession might be due to a warp induced by the magnetic fields in the disk. This has been shown in some theoretical models, though little work has been done to show that this could occur in practice. Regardless, it's exceptional for us to be able to trace a wiggle in a stellar jet across both lobes so close to the source, with a clear symmetry that points to an origin in precession, regardless of the ultimate cause. This may help to explain the rotation signatures and position offsets observed by Coffey et al. previously. The MUSE dataset has therefore allowed us to examine TH28 in unprecedented detail, and this helps to demonstrate an additional way to search for otherwise hidden companions close to young jet-launching stars. So that brings us to the end of this talk on the search for hidden companions around T-Tauri stars. I hope you found it interesting. We welcome any questions you may have, but for now, thank you for listening.